For more information on tutoring, personalized video solutions, or how to support Moof University and the production of more videos, check out moofuniversity.com. Thank you and enjoy. So first up, ionic compounds. But before we start talking about ionic compounds, we have to remember and keep in mind that opposite charges attract while like charges repel. Okay, cool. So ionic compounds are composed of ions. You might be thinking, well, duh, right? Well, specifically, they're composed of a cation, which is positively charged, and an anion, which is negatively charged. Now, these ions resulted because of a transfer of electrons, right? So if we think about a binary ionic compound, what that is specifically a metal, which I'm going to abbreviate as just M, and a nonmetal, which I'm going to abbreviate as NM. Okay. So the metal in a binary ionic compound will, what it does is it loses electrons to the nonmetal to become the cation. Okay, metals lose electrons to become cations. The nonmetal gains electrons from the metal to become an anion. Okay, so the metal loses its electrons to the nonmetal. Okay, let's see an example of this. So let's take a look at sodium metal, which I've got here, and I've shown its electron configuration as everything up until neon and then 3s1. And over here we've got chlorine, right, with its electron configuration neon and then 3s2, 3p5. Okay, and I've drawn both atoms here. This is a sodium atom, this is a chlorine atom. So you'll see here the sodium atom has 11 protons and 11 electrons, so it's neutral. And the chlorine atom has 17 protons and 17 electrons. It's neutral as well. Now, what you should pay attention to is the idea that sodium has one extra electron, right, past its noble gas configuration, while chlorine needs just one more electron to reach the next noble gas configuration, which would be argon. So what ends up happening here is that sodium, the metal, is going to lose an electron to chlorine, the nonmetal. Whoa, that's not right. Nonmetal. There we go. That's right. So what's going to happen is one of these electrons right here will go from one of these 11 is going to go over here. Okay, I'll represent that by putting one electron there. Okay, so the sodium metal is going to lose one electron while the chlorine nonmetal gains one electron. Okay, so what happens to each? Well, the sodium metal becomes a sodium cation, and the chlorine nonmetal is going to become a chlorine anion. Okay, specifically, the sodium went from having 11 electrons to now it has 10, which means it has one more proton than it does electrons, so it's going to have a positive 1 charge. And the chlorine went from having 17 electrons to now 18 because it gained 1, which is one more electron than it has protons, so it has a negative 1 charge. And so now what's going on is we've got a positive charged particle here and a negatively charged particle here, and they're going to be attracted. Okay, that's what this red dotted line between them represents. The red dotted line between them represents the electrostatic force between them. That is, they're now attracted to each other. Okay. Specifically, this is going to be a chemical bond. Even more specifically, it's going to be an ionic bond. Okay. And so notice here a few things is that this sodium cation here has a noble gas configuration, and this chlorine anion has a noble gas configuration as well, the noble gas configuration of argon. So they've both reached electron configurations that are really, really stable, which is why this ionic bond even formed. Okay. Now, also, one thing to keep in mind is that there's overall no net charge because we have a sodium cation, Na+1, and a chlorine ion, also called a chloride ion, and I'll write that here. This is a chloride ion. Okay. And it has no net charge. Na plus, Cl minus, the overall charge is 0. Okay. Another thing I want you to hopefully have noticed is that the sodium decreased in size because it lost an electron, thus increasing the effective nuclear charge, drawing the 10 electrons that are left in a little bit closer to the nucleus. So it got smaller. And the chlorine, gaining an electron, the effective nuclear charge decreased, so those protons are not pulling in with as much force as they were before. So this got bigger. Okay. I hope you noticed that. Okay. Now you'll notice also that I have a little asterisks next to each of these here. And the reason why is that what we've done here is these guys are both monatomic ions. And monatomic ions are just ions that formed from a single atom. Sodium is a single atom. Chlorine is a single atom. They both became ions. Okay. One atom becoming an ion, that's a monatomic ion. Mono referring to one. Now there are cases in which a small group of atoms that are bound together will end up having an overall charge. In that situation, what you'll have is a polyatomic ion. Poly meaning many. Okay. Now, that's just definitions. Now, I want to get back to this idea of this Na plus and Cl minus. Now, Na plus and Cl minus form this Na plus Cl minus or NaCl ionic compound. And what this actually is an array of alternating ions that kind of looks like this. Now, I've drawn it two-dimensional here, just as flat, right? Where these gray positively charged spheres are, or circles, there should be spheres, are the sodium ions, and the green circles represent the chloride ions. And so notice that they kind of, this would be one sodium ion and one chlorine ion, but that's not exactly what the NaCl ionic compound is. What it is it's a crystalline array of alternating ions. It's a crystalline ionic compound. And this is actually supposed to be three-dimensional. And I'm just not an artist. I couldn't really draw it perfectly. But I would encourage you to look up a 3D crystalline ionic compound to kind of see what it looks like. It basically looks like sort of a cube with alternating positive and negative charges. Kind of like what I've drawn here, just in 3D. Okay. Definitely encourage you to take a look at that. All right. Next up. How strong are ionic bonds? Well, the short answer is really strong. They are incredibly strong. Okay. So then the question becomes, how can we compare ionic bond strength between one ionic compound and another? And what we'll do is we'll use what's called Coulomb's law. Okay. So Coulomb's law equation is F sub E equals K times Q1 times Q2 all over D squared. So what do all of these things mean? Now, I'm not going to get into crazy details with this because this is not really physics that we're studying. We're just going to use it for chemistry, so I'm not going to go too complicated in it. But we do need to know what each of these things represents. F sub E is, F sub E is the electrostatic force. Okay. K is Coulomb's constant, which we're actually going to ignore because it's a constant. we don't really need it in the actual value for our purposes. Q1 represents charge number 1. Okay. Q2 represents charge number 2. And D represents the distance between the centers of charge 1 and charge 2. Okay. So electrostatic force is the force between two charges, basically. Okay. So if we have a higher electrostatic force, what does that mean? That means that there is a stronger force between the two charges, whether it's attractive or repulsive, right? If it's a higher attractive force, the two charges will come closer together. If it's a higher repulsive force, they'll repel each other more. Okay, but the point is the strength of the force is Fe, right? Represented by the magnitude of Fe. Okay, so earlier I mentioned that opposite charges attract and like charges repel. So if Q1 and Q2 if the electrostatic force will be an attractive force if Q1 and Q2 are opposite charges. And the electrostatic force will be repulsive if Q1 and Q2 are like charges. Okay. So what we really want to pay attention to is the Q's and this D value. Okay. So what we should notice is that with the electrostatic force is proportional to Q, right? It's proportional to Q. So Q is basically the magnitude of each charge, right? So if we have an increase in the magnitude of charge, that's going to make this number bigger. If that number is bigger, then the electrostatic force is bigger. So an increase in magnitude of charge increases the electrostatic force. What does that mean? At least for our purposes. What that means for our purposes is that ions with more charge will either attract or repel each other more strongly. Okay. So higher magnitude of charge, higher electrostatic force. The opposite would be true. A lower magnitude of charge, weaker electrostatic force. Okay. Now, electrostatic force is also proportional to 1 over d squared, or 1 over the distance between the two charges squared. Okay, so what does that mean? Well, that would mean that a decrease in the distance between the two charges, which means a smaller d value, that would mean that we're dividing by a smaller number, which would make Fe bigger, right? So a shorter distance, or a decrease in the distance between the two charges, will give us a larger electrostatic force. What does that mean? That means that smaller ions attract or repel each other more strongly. Okay, so let's use what we just learned there and apply that to answering this question here. In which case would the ionic bond be stronger? Na bound to Cl or K bound to Cl? Well, I'd have in both of them a Cl, so that's common to both. That can't be where the difference lies. The difference lies between Na and K. Well, if I have Na bound to Cl, that means I have an Na plus ion and a Cl minus ion. And in K bound to Cl, that's K plus and Cl minus. Like I said, the Cl minuses are common to both, so we're going to kind of ignore that. So we're comparing really Na plus and K plus. Well, I noticed that both of them have a charge magnitude of +1. So their differences in their Q's is not going to be much different. Okay. However, their atomic size or their ionic size is different. Okay. What I notice is that if I look on the periodic table that I've drawn here, including only these elements that I'm talking about, I notice that Na is right here and K is right here. K is right below it. And if you recall from the periodic trends, atomic size and ionic size increase down and to the left. So between Na plus and K plus, which is bigger? K plus and Na plus is smaller, right? So since Na plus is smaller and K plus is bigger, what would that mean? Well, if I imagine Cl to be this size, and in both cases it's about the same size, right? Na would be smaller. Let's just exaggerate the point and say Na plus would be like this, and let's just say that K plus is bigger. Let's exaggerate the point like this by making this a lot bigger. If I think about the distance between the two centers of the charges, right? What's a bigger distance? Well, this value here, right? And this one here is smaller. So where would the force be stronger? Wherever the distance between the two is smaller. So I would expect the ionic bond to be stronger between Na and Cl than it would be between K and Cl, because the distance would be smaller. Okay. What about with magnesium bound to fluorine versus sodium bound to fluorine? Well, I'd have Mg2 plus and F minus here, and then Na plus and F minus here. Again, we've got the anion common to both, so that's not going to be where the difference lies, right? So we're thinking about Mg2 plus and Na plus, okay? Well, Mg2 plus, that means the magnitude of its charge is higher, right? It's got a Q value of 2, whereas this one has a Q value of 1, if we think about it just on a relative magnitude of charge, right? So in that case, I would expect the electrostatic force to be larger between Mg2 plus and F minus than I would between Na plus and F minus, right? So the electrostatic force would be stronger between these guys, so the ionic bond would be stronger between Mg and F than I would expect it to be between Na and F. Some of you are thinking, well, aren't they different in size too? Yeah, they are slightly, but Na plus and Mg2 plus are really, really close in terms of size. So that's not where the key difference lies, even though I would imagine Mg2 plus to be slightly smaller, again, because of periodic trends. But here, the difference is really the charge magnitude. Okay. Now the question is, how do we determine chemical formulas for ionic compounds? Well, we must know the ion or ions that the metal and nonmetal readily form. Okay. Now, when it comes to the representative elements, the 1A through 8A elements, we can kind of just memorize this. Okay. Now, the group 1A elements will readily form a charge of +1, 2A plus 2, 3A plus 3. 8A is the noble gases. They will not form charges. Okay. 7A, they'll gain 1, so they'll be -1. 6A will be -2. 5A will be -3. 4A is kind of unique. It could either gain 4 or lose 4, but for all intents and purposes, we're going to take the group 4A elements to not form ions. Okay. So you could probably make sense of this by looking at your periodic table and thinking, okay, if I have this atom, what would it do as far as gaining or losing electrons to form a noble gas configuration? And that should allow this to make sense. Okay. So how do we determine the chemical formulas for the ionic compounds? Well, if you know the ion that those things readily form, it's fairly simple from there. So if I have Mg and F, magnesium and fluorine, what would the chemical formula between them be? Well, I have Mg, magnesium, in group 2A, so it would be Mg2+, and I'd have F is a halogen, group 7A, so it would be F-. So I have to keep in mind also that ionic compounds are always going to have no net charge. Well, I have one ion here with the magnesium with a +2 charge, and I have one fluorine ion with a -1 charge. And I notice here that if I want these guys to combine to give an overall 0 charge, what I would need is two fluorines, 2 of these -1 charges, to get an overall of 2 -1s. So that would be a -2 overall charge, and this +2 charge, and that would give me 1 Mg and two F's to give this formula. Okay, so I'd have the charges balancing out. I have +2 here, and then I'd have -1, but twice, right? Two of those -1 charges to balance out with that +2 charge. Now, you could think about it that way, and you should understand it that way, but the shortcut way is to just do this. If you have Mg2 plus and F -1, what you could do is the crisscross method, and just say that this number will be the subscript for this element here, and this number will be the subscript for the element here. So what you would get is Mg1 F2, but ones do not need to be explicitly written, so that would really just be Mg F2. Okay. So if we did that quicker method for these others here, we'd have calcium. Calcium is group 2A, so that would be Ca2+, and then N, nitrogen, that would be group 5A, so that would be N3-. So the crisscross method, 2, that would be the subscript here for this other element, and 3, that would be the subscript here. So what that would give us is Ca3N2. Okay. And we can also think about this as 3 calcium plus 2 ions and 2 nitrogen minus 3 ions. If we think about it here, I have 3 plus 2 charges, so that would be +6 charge coming from here. And then I'd have 2 -3 charges, that would be a -6 charge coming from here. And the overall charge there, of course, would be 0. Right. Now just the last one here, crisscross method. Mg, group 2A, Mg2+. And then I'd have O is a 6A element, so it would be O2-. So crisscross method. And I would get Mg2O2. But what I would do here is I'd have to reduce this to the lowest whole number ratio. Okay, so this, instead of being Mg2O2, I would divide both of those numbers by 2 because they have that number as a common factor, and I would get MgO, which is a chemical formula that gives me the lowest whole number ratio of cations to anions in what would be that crystalline ionic compound. This value, or this formula specifically, is called a formula unit because it tells me, like I said, the lowest whole number ratio of cations to anions. Instead of saying I have 2 magnesium ions for every 2 oxygen ions, I can just say I have 1 magnesium ion for every 1 oxygen ion in the ionic compound that is made up of Mg2+ and O2-. Anyway, I hope that video was helpful. Thank you for watching. If you found that video helpful, don't forget to like, comment, subscribe, and share with friends. Thank you and happy studying.